Good morning, all. The next topic is Ampere's force law. We have seen that the attraction or repulsion between two parallel current carrying conductors, which depends upon the direction of flow of current, and that is not electrostatic in nature. We have seen magnetic forces, we have seen Lorentz force law. In this topic, we will see what is Ampere's force law. Now consider two parallel wires carrying current I1 and I2 respectively, and consider a small element dl1 in the first conductor that carries a current I1, and consider a small element dl2 in the second conductor that carries a current I2. These two parallel wires are separated by a distance r21. Now, according to Biot-Savart law, the magnetic field at a distance r21 due to an element dl1 carrying current I1, that is given by, that is a magnetic field at a distance r21 due to an element dl1 carrying current I1, that is first conductor, is given by dB, that is equal to mu 0 I1 by 4 pi dl1 cross r21 divided by r21 cube. Now the magnetic field at r21 due to the entire segment of the wire that carries a current I1 is given by integrating dB. The magnetic field at r21 due to the entire segment of the wire which carrying a current I1 is given by integrating the above equation. Now if we integrate dB, it will become B, that is equal to mu 0 I1 by 4 pi integral dl1 cross r21 divided by r21 cube. Here I1 and I2 are steady current, which is constant in magnitude. This is the magnetic field at R21 due to the current carrying wire I1. Certainly, the conductor which carries a current I2 will experience a force due to this magnetic field. Now consider a small element dl2 on the conductor which carries a current I2. What is the force experienced by dl2 because of that magnetic field produced by the first conductor? We have seen Lorentz force law. The force experienced by the element dl2 which carries a current I2 is given by Lorentz force law, that is dF mag. This is equal to I2 cross B dl2. Since we are discussing about a small element dl2, the magnetic force experienced by that small element dl2 is dF mag, that is I2 cross B dl2. Hence, the force experienced by the entire segment of the wire which carries a current I2, which is in the field of the first conductor, is given by integrating dF mag. The force experienced by the entire segment of the wire which carries a current I2 is given by F mag, that is equal to integral I2 cross B dl2. Integral I2 cross B dl2 where I2 is the steady current in the second conductor and B is the magnetic field produced by the first conductor. What is B? B is nothing but mu 0 by 4 pi integral dl1 cross r21 by r21 cube. The magnetic field produced by the conductor which carries a current I1, that is mu 0 I1 by 4 pi integral dl1 cross r21 by r21 cube. Now substitute the value of B and you will get an expression for F mag as integral I2 cross mu 0 I1 by 4 pi integral dl1 cross r21 by r21 cube dl2. Now mu 0 by 4 pi is a constant. You can take it outside the integral. Now the remaining term can be represented as integral I2 dl2 cross integral I2 dl2 cross integral I1 dl1 cross r21 by r21 cube. Some vector signs are missing. So let us put that vector sign. Okay, F mag that is equal to mu 0 by 4 pi integral I2 dl2. Okay, some vector signs are missing somewhere. Okay, I2 dl2 cross integral I1 dl1 cross r21 by r21 cube. This equation is called Ampere's force law. This equation is called Ampere's force law. Now consider the case when the length of the wire is infinite. That is, what is the force of attraction between two long parallel wires carrying current I1 and I2 respectively? We have seen that the magnetic field at a distance s from an infinitely long wire carrying a current I, that is mu 0 I by 2 pi s, and we have to use that relation here to find the force of attraction between two long parallel wires. First, let us draw the diagram. This is the first conductor. This is the second conductor. The first wire carries a current I1 and the second wire carries a current I2, and they are separated by a distance d. And for convenience, let us mark it as 1 and 2, conductor 1 and conductor 2. Now the magnetic field due to an infinite wire at some point d is given by mu 0 I by 2 pi d. Here the current that is passing through the first wire is I1. Therefore, the magnetic field at 2 due to 1 is given by mu 0 I1 by 2 pi d. Remember, this is the magnetic field due to a wire of infinite length. and the field is pointing into the page. And because of that magnetic field at 2, the wire which carries a current I2 will experience a force. What is the expression for that force? That is integral I2 cross B dl2. Lorentz force law predict a force that is directed towards 1. The expression is integral I2 cross B dl2. Integral I2 cross B dl2 is the force experienced by the conductor that carries a current I2, which is due to the magnetic field B produced by the first conductor, which carries a current I1. And we can represent it as F mag, that is I2 cross B dl2. Now consider the magnitude of that force only. Consider the magnitude of that force. The magnitude of the force is F, that is equal to F mag, that is equal to integral I2 B dl2. Integral I2 B dl2. Here I2 and B are constant, so you can take it outside. That is outside the integral I2B into integral dl2. What is B? B is mu 0 I1 by 2 pi d. Therefore, F mag, that is a force of attraction between two long parallel wires, I2 mu 0 I1 by 2 pi d into integral dl2. Now, the force per unit length between two long parallel wire. The force per unit length between two long parallel wires separated by a distance d is given by F mag, that is equal to mu 0 I1 I2 divided by 2 pi d.